Welcome back everyone. So we are at the open methods to find the root of a polynomial. And in this video we are going to talk about Newton-Raphson method, which we already discussed, but here just to uh, touch upon this, I'll just give you the formulas. So Newton-Raphson method, or we can write it as NR, Newton-Raphson. So we want to find out the solution of this f of x is equal to 0. To do that, let us first do the first order Taylor series approximation. So what does it say? That f of x is f of x naught, where x naught is the known value, plus f prime x naught x minus x naught. Now let's assume x is xk plus 1, the value of x at the current iteration, and x naught is nothing but xk, the value of x at the old iteration. That means from the Taylor series first order approximation we will get f of xk plus 1 is nothing but f of xk plus f prime xk x minus xk plus 1 minus xk. So what we are getting is that f of xk plus 1 is equal to f of xk plus xk plus 1 minus xk f prime xk. Now in Newton-Raphson method, at each iteration we assume that we have reached the solution. That means f of xk plus 1 is 0. At each iteration we are saying that this thing is 0. That means from the first order approximation it will become 0 is equal to f of xk plus xk plus 1 minus xk f prime xk, and this will give me xk plus 1 is equal to xk minus f of xk f prime xk. So the recursion formula or the recursive formula in Newton-Raphson method is xk plus 1 will be calculated as xk minus f of xk upon f prime xk. So this is my recursion formula, or this is my basically I will not call it recursion. This is basically the formula coming out of this. Now the condition for this is that f prime xk should not be 0, otherwise this will diverge, it will approach infinity. Now let us understand this with graphical representation of this. So what are we doing here? So let us say this is my curve f of x and I want to find out this thing. So in Newton-Raphson what we are essentially doing is that, so this is my, let us say, x naught, this is my 0th order guess. Then what I am doing here is that I am taking a line interpolation of this, and I am assuming that this is x naught, then this will be x1, and with this line I am saying that at each iteration I have achieved the solution. That means this is the function which I am assuming at each iteration, and I am saying that f of x k is basically 0. So I am replacing this function with this line within this interval. So that is how I am saying that f of x1 is equal to 0. Then only I will get that x1 is nothing but x0 minus f of x0 upon f prime x0. Then at the second iteration, what I will do the linear interpolation at this particular point. And this is how I will reach x2. Then at the third iteration, I will reach this x3. And eventually I will approach xr, that is the true root. So this is the basically graphical representation of this, that since we are doing the first order approximation of function f of x, so that first order approximation of function f of x is represented by this line. Now we are assuming that this line, since this is the line, so we are assuming that at this particular iteration we have found out the solution. That means that line must that means wherever that line is touching the x axis, that is my root for that particular iteration. And with the help of that, I have found out this formula: xk plus 1 is equal to xk minus f of xk upon f of x prime k. So you understood the point, right? That within each iteration I am basically approximating this function f of x with a first order Taylor series approximation, that is nothing but the line, and within each iteration I am assuming that I have found out the solution. So I am saying that wherever this approximated line cuts the x-axis is my solution of f of x for that particular iteration. You understood the point? So that is the idea behind this this Newton-Raphson method. In the next video I will give you one example, and then I will talk about the error analysis of this Newton-Raphson method. If I am able to do that, I will do that also. Thank you.